One neutron of thorium-231 transforms into a proton and ejected an electron as beta decay and an anti-electron neutrino when it is transmuted into proactinium-231. Since half-life of proactinium-231 is much longer than that of thorium-231, we can assume that proactinium is stable within a time interval of 125 hours. We assume that all the proactinium-231 came from thorium-231. So the ratio of the number of thorium-231 in the sample to the number of proactinium-231 in the sample is 1:3. That means that the current number of thorium-231 is 1 and the original number of thorium-231 is 4. Therefore, the age of the sample is 50 hours. S is the monotonically increasing graph. Since S is stable, its number should keep increasing as more daughter D will decay to form S. Since activity is lambda n, the maximum activity is when the number of D is largest, that's around 9 years, as shown in the graph. The maximum activity is 32.3 microcurie. The number of D anytime depends on two processes. One, the rate of production of D from P, and two, the rate of decay of D to form S. Initially, process 1 is larger than process 2, therefore D increases. When process 1 is equal to process 2, D reaches the maximum, and when 1 is less than 2, D decreases. For a period of 30 years, the percent of parent nuclei will have dropped to almost 0, and the percent of nuclei of daughter product D will still be around 30%. The activity from the decay of D can still be determined rather reliably. For a period of 100 years, almost all D will have decayed to S. The activity of D decreases to a very low value, which is almost constant. Thus, the relative activity of the parent isotope and the daughter product D cannot be measured reliably. Therefore, the method would be far less reliable to determine an age for more than 100 years.